Good morning everyone, we're Zizi and Peter. Today we're presenting Gleanmer, a 6 mW SoC for real-time 3D Gaussian occupancy mapping. This work is supervised under our advisors such as Karaman and VLSI. Many edge applications require mapping, which is the process of building a spatial representation of an environment from sensor rays. So consider a 2D example here, where the camera emits sensor rays that lands on the surfaces of obstacles. The endpoint of the rays represent occupied surface, which is shown in red. But the rays themselves, which are the path from the sensor to the endpoint, define the free space, which is shown in blue. Anything beyond the endpoint is unexplored. The representation that captures all three spaces is called an occupancy map. The occupancy map is drastically different than the more commonly known point cloud map, which is shown on the right. So notice that the point cloud is incomplete because the points, which are the red dots, only capture part of the occupied surface. The occupancy map is versatile and enables many key applications. For AR/VR headset, accurate geometry from the occupied region, which is shown in red, allows the headset to occlude virtual object correctly. On the right, a virtual dragon flies behind a real lamp, not through it. For autonomous navigation, the free region defines where a robot can safely traverse. On the right, this traversal path is highlighted in white, which needs to be contained within the blue free region. Constructing a 3D occupancy map is much more challenging because the number of sensor rays is quite large and scales with the resolution of the depth images. A map is constructed from a large sequence of images, so to simplify, consider a single image shown here, where each pixel represents the distance of the object from the camera. Now this image is only 0.6 MB and can be represented by a large point cloud using 2 MB. To compress this point cloud, we can quantize the space into voxels, which are cubes shown in red. Each voxel exploits spatial correlation, where many neighboring depth points lie on the same surface, so they get bundled into the same cube. However, each voxel is uniform in each axis direction, regardless of the underlying geometry. Thus, voxel maps are still very large. Even though the geometry here is 147 kilobytes for the single image, the size of the map quickly scales to megabytes and even gigabytes with thousands of images. Alternatively, Gaussians can be used as a more compact representation than voxels. Now each Gaussian is parameterized by mean, mu, and covariance matrix sigma. On the left, we plotted a Gaussian distribution in 1D, which is a well-known bell curve. The peak of the distribution is mean, and the width of the distribution is a variance. In 2D, the distribution looks like a small hill on the right. Now if we were to cut the distribution with a red line in 1D and a plane in 2D, we see that the iso surface, where the plane and the distribution intersects, looks like an ellipsoid, which encloses the majority of the distribution. In 3D, we can use each Gaussian ellipsoid to enclose the geometries. So on the right, we can see that the Gaussian map requires only 9 kilobytes. This is 16x more efficient because each Gaussian can change its shape and orientation to flexibly adapt the underlying geometry that is typically represented by multiple voxels. Since each Gaussian map per image is compact, the similar trend holds for a much larger map constructed from multiple depth images. For this city-scale environment, our Gaussian-based map consumes 840 kilobytes, which is around 13x lower than the voxel-based map. Beyond compact storage, efficient map construction is equally important on edge devices. Therefore, our lab previously introduced GMMap in our 2024 TRO paper, which is one of the most memory-efficient Gaussian mapping framework available. GMMap's construction pipeline starts as a sensor input, a depth image, where each pixel encodes the 3D point at which a sensor ray hit an obstacle surface. If we were to zoom in to the highlighted curtain region, the corresponding 3D points lies roughly on the same planar surface, shown here as red dots. Spatial correlation drives the entire map construction hierarchy from depth pixels to Gaussians. At hierarchy 0, which we call H0, we have the depth pixels. Now, pixels that lie on the same planar surface have similar slope, so that they are converting into lines at H1. Then lines that themselves lie close to each other are fused into accelerated Gaussians at H2. So the conversion is progressively more compact as pixels become lines, lines become Gaussians. And critically, the free space is converted in parallel. The rays that produces the depth pixels at H0 sweep through the free space along their path. Therefore, those rays aggregate into free Gaussian wedges at H1, and then those wedges become the free Gaussian bases that combine into free Gaussians at H2. Here's a summary of the data volume flowing through the construction pipeline from H0 to H2. At H0, the raw depth pixels and rays are around 3 megabytes per image. So at the typical camera frame rates of 60 to 100 fps, that's quite high at 180 to 300 megabytes per second. H1 compresses this 10x into lines and free Gaussian wedges, which are around 300 kilobytes per image. H2 fuses them into Gaussians at just 18 kilobytes per image. That's a 170x reduction overall. Once we have Gaussians per image, we'll fuse and accumulate those Gaussians image by image into a global map. The size of the global map is around 167 to 850 kilobytes. Note that this is not per image, but the entire map of the scene. So after the map is constructed, the downstream applications will query the map as 3D locations of interest via a process called regression, which computes the occupancy probability at each of the query locations. In traditional mapping frameworks, memory typically dominates the conversion process from H0 to H2 due to the footprint required to store large amount of primitives, especially at H0. GMMap is especially designed to reduce the storage of those primitives due to the single-pass streaming-based processing. Therefore, the conversion process is only dominated by arithmetic computation that scale with the data volume of those primitives. So even though Gaussians at H2 are the most compact primitives, they're not dominating the memory operations because the global Gaussian map grows and accumulates Gaussians across many images. In addition, the Gaussian operations, such as fusion and regression, become area-dominated because they demand precision-heavy floating-point arithmetics. To resolve those challenges, we present our chip Gleanmer in 16nm CMOS, which to our knowledge is the first fabricated SoC for energy-efficient occupancy mapping. This chip constructs maps from depth images at least 88 frames per second, queries up to 1.3 million coordinates per second while using just 6 milliwatts of power. Here we have shown a wide range of devices that require occupancy mapping with power budget from 28 milliwatt to 70 watt. But the existing solutions don't serve all those devices. If we were to run GMMap on ARM Cortex A57 CPU, it requires more than 4 watts to run in near real time. OMU, the prior occupancy map accelerator, runs voxel-based octomap at around 250 milliwatts, which exceeds the power budget of platforms such as microdrones, blimps, and RoboBee. Our Gleanmer at 6 milliwatts really opens up the application spectrum, bringing real-time occupancy mapping within reach for even insect-scale platforms. So next, we will delve deeper into the details of Gleanmer. So we start first with its architecture. This is the Gleanmer's SoC architecture, which includes the CPU for configuration, system memory for holding the map, external IOs for transferring depth images, and the GMMap accelerator for mapping. The GMMap accelerator is composed of 3 engines. The Gaussian generation engine handles the arithmetic-dominated H0 to H2 conversion. The fusion and regression engine handles the area-dominated Gaussian arithmetics. Finally, the Gaussian management engine handles the memory access-dominated global map storage and retrieval from the system memory. We have 2 contributions that resolve the challenges with arithmetic, memory, and area. Since the primitives are more compact as we go up the hierarchy from H0 to H2, we can reduce the volume of work by transforming the workload from H1 to H2 at the Gaussian level. And we call this efficient hierarchy conversion, which significantly reduces arithmetic intensity. So now I will hand it off to Zixin, who will explain this contribution in more details.
Thank you, Peter, for the introduction. Now let's start from contribution 1. Contribution 1 is related to the Gaussian generation engine. This engine converts pixels and rays at H0 into Gaussians at H2. If we were to directly map the original GMMap algorithm to specialized hardware, here's what the architecture looked like. Pixels becomes lines per row, lines split into two parallel paths. One path fuses lines into occupied Gaussians. The other path generates free Gaussian wedges and then fuses them into free Gaussian bases. We can see that the compute of the wedge path scales with the number of wedges, which scales with the number of line segments. The number of line segments are in the thousands, and thus causing the wedge path dominates 65% of the map construction energy. In Gleanmer, we shift free Gaussian basis generation to higher level by eliminating the wedges. Since occupied Gaussians represents the underlying pixels and lines well, we can sample a small set of rays from occupied Gaussians to represent the free space between the occupied surface and the camera, and use them to directly generate the free Gaussian bases. As a result, the optimized algorithm generates free Gaussian bases from only hundreds of occupied Gaussians instead. And here's the optimized hardware. The entire data path related to the free wedges now can be removed. This reduces energy by up to 63% for map construction while maintaining accuracy. After most of the workload is shifted to the highest Gaussian level with hierarchy conversion, we can then focus on optimizing the workloads for Gaussians. This leads to our second contribution on applying reduced precision and exploit data reuse on Gaussians to reduce area and memory access intensity. Contribution 2 has two parts. First, the fusion and regression engine. This is the area dominating engine. To reduce the area, 19-bit and 22-bit floating point arithmetic are used for fusion and regression. The only exception is covariance matrix update, which requires 32-bit precision. On the left, we have the equation of the Gaussian where the inverse of the covariance matrix is on the numerator. The eigenvalue of this covariance matrix is the thickness of the Gaussian surface. If we were to compute the covariance using reduced precision, the eigenvalue can become exactly 0, which degenerates the Gaussian and makes this matrix non-invariable. This results in slight degradation in map accuracy, and most importantly, Gaussians representing the same object across images could not be fused properly and leads to around 10 times increase in the final map size. With reducing the precision properly, the area of fusion and regression engine is reduced by 49%. Now the second part of contribution 2, the Gaussian management engine. This engine is in charge of allocating and retrieving Gaussians from the global map, and the memory access energy is dominated by this engine. To reduce the data movement in the system, the first idea is that we can cache Gaussians especially close to the interested trajectory. Let's see a simple example. On the left-hand side, we show a Gaussian map under a bird-eye view. During incremental construction, the robot moves from one location to the next location. The camera, shown in orange, see similar set of Gaussians, highlighted in strides. We see this access pattern has pretty good temporal locality. The similar temporal locality is seen for map query. Here we plotted a trajectory in black. Along the trajectory, we want to query coordinates, shown in orange star, for checking whether these coordinates intersect the occupied Gaussians. The same set of Gaussians in strides are accessed across most query coordinates. To exploit the temporal locality in both cases, a 44 kilobyte Gaussian cache is used to increase map construction throughput by up to 7 times and map query throughput by up to 9 times. In addition to caching, We can also reduce the number of memory accesses by reusing Gaussians across multiple Curie coordinates. To enable Gaussian Curie in logarithmic time, the Gaussians are stored in a tree of bounding boxes called an R-tree. An example of the R-tree is shown on the left, where the leaf bounding boxes are shown in green and the root is in gray. If we were to traverse this tree for the 3 stars coordinates around the trajectory, the total path length of 3 traversal, shown in red, sums up to 8. Since the same set of red and blue Gaussians are retrieved multiple times across 3 coordinates, we have a lot of redundant memory accesses. To eliminate redundant memory accesses to the similar set of red and blue Gaussians, we can use a purple bounding box B across all 3 coordinates to retrieve both Gaussians in a single tree traversal. Then, these Gaussians are reused across all 3 coordinates, and so the resulting path length is reduced by half. When performing a single R-tree traversal across 16 nearby Curie coordinates, the Curie energy reduces up to 81% with less than 2% area overhead. Next, we talk about the chip specifications and comparisons. Here's the chip specification for Gleanmer. Gleanmer is fabricated in 16nm CMOS. It's a 2x2 die with 622 kilobytes of on-chip SRAM. It can run map construction at 88 to 331 FPS, and can run map query at 540K to 1.3 million coordinates per second. The power for running these tasks are all under 6 milliwatts. We evaluated Gleanmer on 3 very different environments: an indoor office room, an unstructured forest scene, and a large city scene. Across all 3, the chip holds map accuracy steady while shrinking the map size thanks to the reduced precision. We can see the occupancy map of a full city block can be stored in less than 400 kilobytes and fully constructed on chip. In short, reducing Gaussian parameters to 19-bit floating point preserves map accuracy while shrinking map size by at least 44%. Here are the maps Gleanmer constructed across the 3 environments. The top row shows a cross-section of the occupancy map. Red regions are where the obstacles are, blue regions are free space, and yellow regions are explored regions. The bottom row zooms into a particular location in each environment to show the 3D structure. The red ellipsoids are the Gaussians. You can see how they covered the underlying point clouds pretty well. Now to construction energy. We mainly reduce energy from Gaussian generation engine, shown on the left. On the right, we can see the construction energy is reduced by 22 to 63% thanks to efficient free Gaussian basis generation from occupied Gaussians. The savings is environment dependent. The savings are larger if 1 Gaussian corresponds to more wedges in the original algorithm. For the area reduction, the real savings come from Gaussian generation engine and fusion and regression engine. On the right-hand side, we show the area reduction of each contribution. Starting from the node optimization, efficient hierarchy conversion gets us 16%, mostly from removing the wedge processing path from Gaussian generation engine. Then, reducing Gaussian precision gets us all the way to 38% area savings, mainly from reducing logic area in the fusion and regression engine. Last is the Curie energy. The energy reduction comes from the Gaussian management engine shown on the left. On the right, we can see the Curie energy is reduced by 74 to 81% thanks to the batch currying. This works especially well because Gaussians cover a large spatial region, so that a small batch of nearby coordinates overlap a similar set of Gaussians. Here's our validation setup. On the left is a full setup of the chip validation. We can see a 3D occupancy map being constructed and visualized as the frame comes in. And on the iPad, we can see the real-time power consumption. On the right, we can see the chip testing platform. The Gleanmer chip is in the red box part. So Gleanmer streams depth images into the chip from the laptop and constructs a real-time 3D occupancy map on the chip testing platform. Now, let's see how Gleanmer compares against prior hardware. There are 2 reference points: the Jetson TX2 running our same GMMap algorithm, and OMU, which is a prior ASIC for Octomap, a voxel-based mapping. To sum up, with comparable accuracy, Gleanmer consumes at least 341 times less power than Jetson TX2, and 44 times less than OMU. In summary for today's talk, first, Gaussian mapping converts data across 3 levels of increasing compactness, from depth pixels and rays to lines and wedges, and finally Gaussians. Gleanmer's 2 co-design contribution is as follows. First, efficient hierarchy conversion. We shifted free Gaussian basis generation towards higher level using occupied Gaussians, reducing the volume of work. Second, amplified optimizations for Gaussians. We apply reduced precision, caching, and batch query to the Gaussian workloads and reduce the area and exploit data reuse. With a co-design method, Gleanmer delivers 63% lower construction energy, 81% lower energy on query, and 38% smaller area versus the baseline. Altogether, Gleanmer is the first fabricated SoC for real-time 3D Gaussian mapping under 6 milliwatts, enabling 3D occupancy mapping on a very wide range of edge devices. Last, thanks to our sponsors, the MathWorks Fellowship, Amazon, NSF CPS, and Intel USP. Thank you. Thanks for your attention.